Okay, so in last class we talk about that pole zero placement methods for designing that IIR filter, but you have seen there is a lot of limitation on using that pole zero placement methods. So, the best possible way to design IIR filter is called analog filter design method. What is analog filter design methods? Because if you see that analog filter or this methods is the simplest method, because that analog filter design methods are available long back before the digital filter was came out. So, design methods of analog filter is well established. So, there is a lot of prototype to design analog filter, Chebyshev, Butterworth, elliptical. So, all kinds of prototype filter design methods are available and which are already proven that those are the very good methods. So, analog filter design methods of IIR filter design, what we do? First we design that analog filter for the given specification. So, whatever the filter specification is given, I design that analog filter for that specification. What is the design methods? Analog filter means H of S. H of S means Laplace representation of transfer function of the analog filter. So, we design H of S using analog filter design methods. Then what we will do? We convert H of S to H of Z using any one of these two methods, either bilinear transformation or impulse invariance methods. So, analog filter design method can be summarized like that. First, you design the desired analog filter transfer function, or I can say from the given specification derive the analog filter transfer function H of S. Once I get the H of S, I can convert H of S to H of Z using any one of the methods, either bilinear transformation or impulse invariance methods. Once we get that Hz, I can implement it using discrete structure 1 and discrete structure 2 methods. Any one of that I can use and I can implement in the computer. So, analog filter design methods of IIR filter design summarized in basic 3 points. One is design the desired analog filter and derive the transfer function H of S. Once you get that, steps to convert H of S to H of Z. Step 3, once you get the H of Z, implement H of Z using computer using structure 1 or structure 2 methods. Okay. So, let us say first talk about that how to design analog filter. In this lecture, I will not details cover on that, but I will summarize what is there and how this can be used for design and given analog filters for a given specification and an analog filter. So, there are 3 methods are there: Butterworth, Chebyshev, elliptical filter design. I will cover these 2 methods. This method you can see from the book, because analog filter design methods are taught in many classes. I do not want to length it, because unless this again it will require another week of lectures. So, here also I will not cover the details of Butterworth filter design method. I will cover only the point which is required to derive the transfer function of the filter from a given specification. Then we straight go to the how to design the IIR filter. Okay. So, let us talk about the Butterworth filter design method. Okay. So, what is that? Now, let us the magnitude square frequency response for the Butterworth low pass filter. So, we design the ideal low pass filter, then shift it for desired kind of high pass filter, band pass filter. So, I want to design a low pass filter using Butterworth design methods, where the omega p is the pass band edge frequency. Omega p is the pass band edge frequency, and the magnitude response using Butterworth design will be given like this: H of omega square. This is a magnitude response. So, magnitude response means frequency. I have taken that inverse transform Hn is converted to the frequency domain, and I have taken that magnitude of that frequency domain. So, there is a phase and magnitude. So, I plot the magnitude part. So, if I take the magnitude response, it will come 1 by 1 plus psi square, this is called epsilon square into omega by omega p. This omega is analog frequency. So, this is radian per second, and this is not radian per sample. That is why I write this omega, not write this omega. This omega is radian per sample. So, this is the difference. This is digital and this is analog. So, this is discrete frequency, normalized discrete frequency, and this is analog frequency. So, if the omega p is my passband edge frequency in analog passband edge frequency, then the magnitude response is 1 by 1 plus epsilon square omega by omega p to the power 2n. Okay. Where epsilon is the ripple factor, omega p is the 3 dB cutoff frequency or passband edge frequency, and n is the order of the filter. So, if order of the filter is n, the passband ripple is epsilon, and omega p is the passband edge frequency, then the magnitude response, square magnitude response is this one. Okay. Now, at omega equal to omega p, so if you see the filter is look like this, let us say this is my 3 dB down. So, this is my omega p. So, at this axis is omega. So, at omega equal to omega p, then I can say this one omega by omega p is equal to 1, and that is nothing but a 1 minus delta p whole square, or I can say minus ap decibel. Okay, delta p is the ripple in the passband. So, if I convert into the dB, 20 log this one, so omega by omega p becomes 1. So, this is nothing but a 1 by epsilon square, this function 1 by epsilon square, 20 log is equal to minus 2 ap. Now, I know 1 by epsilon square equal to 10 to the power 0.1 ap. Now, if the ap is 3 dB down, so ap is 3 dB minus 3 dB. So, ap is 3 dB down, then epsilon square is equal to 1. So, epsilon is equal to 1. So, transfer function becomes this one. So, is omega p is defined at 3 dB down. Now, let us say omega p is not defined 3 dB down, 4 dB down. Then I can get an epsilon, the passband ripple. Is it okay? So, I know that Butterworth transfer function, that is of a filter design, this is the magnitude response of the Butterworth filter. So, now I know, let us say if I say that omega is replaced by j omega, so it is 1 by 1 plus the epsilon is equal to 1. I said my filter specification is designed on 3 dB down, omega p is designed at 3 dB down. So, epsilon is equal to 1. So, I put that epsilon is equal to 1. So, this is my omega h omega square. So, what is h j omega square? Is nothing but a, so it is a complex function. So, it is square is nothing but a product of complex conjugate. Magnitude square is nothing but a product of complex conjugate. So, if I do the complex conjugate product, then I can write down h j omega into h complex conjugate of j omega. Now, you know the complex conjugate of the j omega from the frequency transform property is nothing but a h of minus j omega. So, it is nothing but a minus j omega. Now, what is Laplace domain? What is Laplace transform? Laplace transform is nothing but a also a complex plane which is called S plane. So, S plane, this is j omega and this is some real part. So, S, if I replace S by j omega, so j omega is replaced by S, that means real part of the Laplace domain is 0. So, in that case I can say it is nothing but a Hs into h of minus S is equal to 1 by S by j omega p to the power 2n. Now, if I see if this is my transfer function of 2 Hs, so order of the is 2n, then I know the order of Hs is n. Hs into Hs is order of 2n. That means order of the filter transfer function Hs is nothing but a n. Okay. Now, how do I get the pole of this Hs? So, pole is nothing but a solution of this equation. So, I have to solve this equation. So, 1 plus s plus j omega p to the power 2n is equal to 0. So, if I want to solve it, so j omega s by j omega p to the power 2 minus 1. So, s is equal to minus 1 to the power 1 by 2n into j omega p. So, those are the pole position, the solution pole position. Now, h of s has a n number of pole because order of the filter is n. So, 1 minus 1 to the power 1 by 2n. This small n is varies from 0 to n minus 1. So, order of the pole is n. Okay. Now, if I want to write down the generalized form of this part, so what is the generalized form of this part? I am not writing this one because this one I will take a slide here, then I show you how can you draw the generalized form. So, I said this is the generalized form. How do I derive it? Unless you know that, you may not be, you may be not understand how this kind of expression will come. So, what I said minus 1. So, minus 1 can I implement using e to the power something? So, if I say e to the power j pi, what is e to the power j pi? E to the power j pi is nothing but a cos pi plus j sin pi. So, which is nothing but a minus 1. So, minus 1 can be said e to the power j pi. So, I can say e to the power j pi divided by 2n, that is this one. This portion can be synthesized like this one. Now, since I have to, for n is varying, n is the order of the pole. So, if the nth pole is there, so n is varies. So, where is my other poles? So, for that purpose, I said let us k equal to 0, 1, 2. So, if I say that, then I can say it is nothing but a j pi by 2n into 2k minus 1. If you see k equal to, see all the time it will be minus 1 to the power 1 by 2n. K equal to 0, same thing, k equal to 1, k equal to 2. Okay. Now, what is j omega p? So, omega p is constant, okay, the cutoff frequency. What is j? How can I synthesize j? So, e to the power j pi by 2. What is the value? Cos pi by 2 plus j sin pi by 2. So, if I say this is 0 and this is 1, so it is nothing but a j. So, I can say e to the power j pi by 2 into omega p. Okay. So, now if I add this one, so e to the power j 2 pi by n into 2k plus 1 plus j pi by 2 into omega p. Now, if I said 2n will be there, if I say that e to the power j pi by 2n I have taken out. So, it is nothing but a 2k minus 1 and this plus is nothing but a n. So, it is nothing but in the form of omega p into e to the power j by 2n 2k plus n minus 1. So, those are the pole position I can determine if I know n, if I know n. Order of the filter I know known and omega p I known. Then I can calculate S0, k equal to 0, S1, S2, S3, I can calculate all the poles. Okay or not? So, when I design Butterworth filter, from the given specification, if the omega p is defined at minus 3 dB, then I know epsilon is equal to 1. That means passband ripple is equal to 1. And once passband ripple is equal to 1, I know how to define the pole position from this equation. This is the equation to define the pole position. Then what is the relationship? How do I design the transfer functions? So, for a given order of the filter, I know the pole position. Now, pole position Sk I know. So, what I know? I know S0, I know S1, I know S2. Now, if the filter want to be a stable filter, stable and causal filter, then all the pole must be located in the left hand plane of the S plane. This is S plane. So, this side, all the pole must be located in this side. Stable. So, I can say this side means I can say it is nothing but a H of S is nothing but a 1 by product of S minus Sk into S minus Sk star. Why I given star? Because if the filter is real, if the poles, if the filter transfer function is real transfer function, then this pole will be occur in complex conjugate. That means, let us say A by S minus B. So, is real. So, in that case, that pole will occur in complex conjugate form. That is why I said it is a product of complex conjugate pole. So, when I say a real filter with order n equal to 4, that means there will be a 2 complex conjugate pair will be there. So, if the first one is A plus JB and second one is C plus JD, then third one will be A minus JB and another one will be C minus JD. All will occur in complex conjugate manner. So, product of this will be the transfer function of Hs. So, once I know Sk, I can derive the transfer function Hs and it will always minus, because the poles are located in left hand side of the S plane. Now, I come the order of the filter required. So, how do I define the order of the filter? How do I define what should be the order of the filter from the given specification? So, what is given in the specification? It given passband edge frequency omega p, it given stop band edge frequency omega s, it given stop band ripple. So, stop band ripple is delta 2, passband ripple is delta 1. So, stop band ripple is given, stop band edge frequency is given. So, at the stop band edge frequency, what is the square magnitude? Because h of omega, I know h of omega square is nothing but a 1 by 1 plus epsilon omega divided by omega p to the power n. So, at omega equal to omega s, so at omega is equal to omega s, that means at this point stop band edge frequency. So, the amplitude is delta 2. So, I can say this is nothing but this side is nothing but a delta 2 square and this side is 1 plus epsilon square into omega s by omega p to the power n. Now, if I say that omega p is defined at 3 dB down, then I can say epsilon is equal to 1. So, I take epsilon is equal to 1 unless I have to calculate the epsilon value. Now, from there I can calculate the n. So, if I know delta 2, I can calculate the n. So, I can summary I can say n delta 2 epsilon and Qs and Qp are characterize the Butterworth filter design requirement. So, if I will be able to determine the Butterworth filter transfer function, if I know omega s, if I know omega p, if I know delta and if I know epsilon, n I can derive. Or if the n is given, then I can say what should be the passband ripple, vice versa. So, let us get I think there is an example. Let us take an example. I said determine the order and pole of a low pass Butterworth filter that has a minus 3 dB bandwidth at 500 Hertz and attenuation of 40 dB at 1 kilohertz. So, what it is? First you draw the picture. So, I can say there is a pass band at 3 dB, let us say this kind of things. At 3 dB down, let us say this is 3 dB down. So, this is omega p is equal to 2 pi into Fp. So, Fp is equal to 500 Hertz. So, I can say omega p is equal to 2 pi into Fp is equal to 1000 pi. So, if this axis is omega. Now, this is let us say stop band edge frequency. This attenuation, so this is the attenuation, that attenuation is 40 dB. This axis is mod of h omega whole square in dB. Okay. So, this is 40 dB down, this is nothing but a omega s. So, what is omega s? Omega s again it is nothing but a 2 pi Fs. What is Fs? At 1 kilohertz. So, it is nothing but a 2 pi into 1 kilohertz, it is 2000 pi. How much attenuation? 40 dB. So, what is delta 2? So, 40 is equal to minus 20 log 2 delta 2. So, I can say delta 2 is equal to 0.01 because this. So, I can say 40 is equal 40 by 20 minus is equal to log 10 delta 2. So, I can say this is nothing but a 2. So, it is nothing but a delta 2 is equal to 10 to the power minus 2, which is nothing but a 0.01. So, once I know the delta 2, I can put delta 2 in this equation. So, it is nothing but a log 1 by delta 2 whole square. So, 1 by delta 2 means 10 to the power 2 whole square means 10 to the power 4. So, 10 to the power 4 minus 1 I can neglect. So, 10 to the power 4 means 4 divided by 2 into log omega s 2000 divided by 1000 log 10 2. 2 into log 10 2. So, 4 by 2 into log 10 2, how much will come you can determine, and let us say this is equivalent to 4. So, n is equal to 4. So, once I said or 3 whatever is coming. So, n equal to 4. So, order of the filter is 4. So, I know xk is equal to omega. So, I can say S0 is equal to omega p e to the power j pi divided by 2 j pi by 4, 4 into 2 means pi by 8 into k equal to 0. So, it is nothing but a 4 minus 1. So, it is nothing but a omega p e to the power j pi by 8 into 3. So, it is nothing but a omega p e to the power j pi by 3 pi by 8, which is nothing but a omega p into cos 3 pi by 8 plus j sin 3 pi by 8. So, omega p you know you can get that complex pole, let us say a plus jb. So, I will get a plus jb. Then put k equal to 1, k equal to 2 and k equal to 3. You calculate S0, S1, S2, S3. Once you calculate it, what is the transfer function? What is the transfer function Hs? Hs is nothing but a, I can write down in here, Hs is nothing but a 1 by S minus S0 into S minus S1 into S minus S2 into S minus S3. You can find out that S0, S1 you calculate, you can this S2 and S3 are the complex conjugate of S1 and S0. You can find out also. So, I have designed. Okay. So, this is the Butterworth filter design. Let us say another example I give you. Example first give, then I come to the step. So, what is the example? Design a low pass Butterworth filter with a maximum gain 5 dB, a cutoff frequency 1000 radian at which the gain is 2 dB. So, let us first I draw the frequency response of the filter. this axis is the omega, this axis is the mod of h omega whole square in dB. Okay. So, what I said? I said this is 5 dB, gain of 5 dB, then it is decreased to 2 dB. So, it is here it is 2 dB. So, this is 5 dB. So, how much is decreased? This decrease is 3 dB. So, here it is omega p, and then again it is decreased to minus 25 dB, minus 25 dB. Here it is minus, this axis is minus 25 dB, which is omega s. I have to design this filter using Butterworth. So, what I have to find out? I have to find out h of s. So, what is omega p? Omega p is equal to 2 pi into fp. So, what is the fp? fp is 1 kilohertz. So, it is into 1 kilohertz. So, it is nothing but a 2000 pi. What is omega s? Omega s 2 pi into fs. Fs is equal to 5000 radian, 5000, oh sorry, it is given in radian per second. So, I do not require to multiply. So, it is already given, omega p is equal to 1000 and omega s is equal to 5000. This is given in radian per second. If it is given in hertz, then I have to multiply 2 pi. Okay? So, omega p is given, omega s is given. Now, if you see, since it is minus 3 dB down, I can say epsilon is equal to 1. Okay. Now, how much is the total dB down? Minus, so here it is there in 5 dB, it is come to minus 25 dB. So, total attenuation is minus 25 and also this 5. So, minus 5 is equal to minus 30 dB is the total attenuation. So, I can say minus 30 is equal to 20 log delta 2. So, delta 2 is equal to 10 to the power minus 3 by 2. So, you can calculate delta 2. Once I know the delta 2, I can calculate n. N is equal to, you know the formula for calculating n. N is equal to log 1 by delta 2 whole square minus 1 divided by 2 log s divided by omega s by omega p divided by omega p. So, I can calculate n. Let us say n come around 5. Then what is the transfer function? So, transfer function is nothing but a sk. I have to find out sk. So, s0 is equal to omega p into e to the power j pi by 2n. So, if it is n equal to 5, it is 10 into 2k. 2k equal to 0, 2 into 0 plus n into 5 minus 1. So, it is nothing but a omega p e to the power j pi by 10 into 4. So, it is nothing but a omega p e to the power j pi by 5, 2 pi by 5. So, which is nothing but a S0 is equal to omega p into cos 2 pi by 5 plus j sin 2 pi by 5. So, I get a plus jb format. Similarly, I will calculate S1, I will calculate S2, and then I said this Hs, transfer function is Hs is equal to 1 by S minus S0 into S minus S1 into S minus S2 dot dot dot, how many poles are there as per the order of the filter. So, I get that Hs. Okay. So, once I get Hs using Butterworth filter design, I can convert to Hz and I can design the IIR filter. Okay. Now, the design step for the Butterworth filter in summary. So, convert the filter specification to their equivalent in the low pass prototype. So, what I said, suppose I have to design a band pass filter. Band pass filter also can be designed using a low pass filter. So, this is the band pass filter. I can say this is a low pass filter here. So, if I design this one as a low pass filter and then shift it into certain frequency, I get the band pass filter. Details I will discuss at the end of this week lectures, how this can be done. Okay. So, first design the prototype, determine the equivalent prototype of the low pass filter. So, now from AP, attenuation in the pass band, from there you find out epsilon. Most of the cases epsilon will be 1 if the omega p is defined at minus 3 dB down. Then you determine the delta, from delta to determine the filter order. So, if the stop band attenuation is given, you calculate the filter order. So, determine the left hand poles using the equation and construct the low pass filter prototype and transfer function. Okay. So, Laplace domain, always poles are in the left hand side, not right hand side. If it is right hand side, filters becomes unstable. So, all the poles or position is left hand side, that is why it is S minus Sk, S minus Sk. And if it is the transfer function is real, I can say the poles will be occur at complex conjugate manner. Okay. So, this is the summary for design of Butterworth filters, analog filters. Then next class I will talk about Chebyshev filter design, analog filter design. Okay. Thank you.